Mrs. Özlem Yeşiltaş to present higher order supersymmetric models in quantum mechanics. Thank you.
Thank you for everything, and it's wonderful for me, and it is a great honor for me to give this speech to you. And after these excellent presentations, it is me who should be in the shadow, I should say. Today, I want to talk about higher order supersymmetric quantum mechanics. Why higher order? Because there are many benefits. Supersymmetric quantum mechanics is one of my research topics. Mainly. First, I want to talk about very basic principles. After that, I want to talk about higher SUSY, the direct approach, because there is another approach, which is iterative approach. The confluence and non-confluence, the standard supersymmetric approach. And I shall give some examples. At the end, we can conclude the results, or we can talk about the future studies about this topic. Of course, the cornerstones, I want to show you the Dirac, who first introduced the factorization of the Hamiltonians, and then Schrödinger applied his model to the Coulomb's problem, and then Infeld is the one, he was the one also developed this factorization method with the very modern mathematical tools. And Ramon uploaded a physical meaning to the supersymmetric quantum mechanics, because it's not the thing in high energy physics or particle physics. So I mentioned the very basic quantum mechanical tool here. Ramon proposed a wave function for free fermions, which is based on the dual structure for bosons. So the particles come in super multiplex. After that, Witten and his very precious contributions were done. And I can give a list of developments with the modern techniques. So there is a list of few precious contributions from the scientists. So one can classify this supersymmetric quantum mechanics in four, as you see, the titles are factorization, shape invariance, there is integrability condition especially, Darboux transformations and intertwining methods. The hierarchy of the Hamiltonians this is generally used in shape invariance models, but in higher order SUSY, we generally use factorization and Darboux transformations, especially Darboux transformations and intertwining methods. Let's look at the basics. N2 means, N equals to 2 means, we have two supercharged operators. So these Q's are known as supercharged operators. The Q and the Q dagger are responsible converting the bosonic state into fermionic states and fermionic states into bosonic states. So the supersymmetry is a tool which converts bosons into fermions and fermions into bosons. Of course, this supercharged operator is commuting with the Hamiltonian, and Hamiltonian operator can be shown. It has the components H1 and H2. We have H1 and H2 Hamiltonians. I want to show these Hamiltonians. Oh yes, here it is. You can see H1 and H2 are the superpartner Hamiltonians, and they can be factorized, right? So the ground state of the Hamiltonian can be shown here, and of course there are the ladder operators up and down. So the effect of the ladder operator on the ground state should be equal to 0. And one can find a function Wx which is known as superpotential. Superpotential here is expressed in terms of the ground state wave function. So if you know the ground state wave function, you can probably get the superpotential. And of course, using your ladder operators, one can say that the wave functions of the Hamiltonians, I mean the partner Hamiltonians, let me say H1 and H2. So this H1 will correspond to the fermionic, and H2 will correspond to bosonic Hamiltonian, or maybe vice versa. H1 is corresponding to the bosonic, and the H2 is corresponding to the fermionic Hamiltonian operator. And you can see the operator effects on the solutions of the system. So these are very basic and very well known details of the supersymmetric quantum mechanics. For the, of course, unbroken SUSY case, the ground state of the Hamiltonian, one is normalizable, but the other Hamiltonian, as you see in this picture, the other Hamiltonian has a missing state. The state is missing, so this means that the wave functions are not normalizable. Alright, so you can see these two partner Hamiltonians, which are isospectral, and the energy relations can be found, and also the wave function solutions can be found very easily. Now, in that picture, I show you a shape invariant potentials. Like the superpotential is given by a parameter times x cubed, and you can generate the partner potentials, and you can see the graphs. So these potentials have a common energy spectrum. So about energy levels, we can say that the lowest energy of the bosonic Hamiltonian is 0, and this is corresponding to a physical state with 0 bosons and 0 fermions. All right. Okay, so this is very brief basics of the supersymmetric quantum mechanics, but a few questions may appear in your mind. For example, one of them, how could we get more detail and information of the behavior of the energy levels and also solutions? Maybe you may wish to have a more complex potential. Maybe you wish to find bound states of potential in relativistic or non-relativistic quantum mechanics. Of course, so we wish to give an order for the energy levels. If I have, for example, E1, E2, E3, so what's the relationship between the energy levels? So the higher order supersymmetry can give us an opportunity to understand what's going on in the spectrum. So, are there more general potential families? We still don't know. So this could be another question, especially the more general huge potentials can be generated, but their partners are generally the ones whose spectrum and solutions are very well known in quantum mechanics. So there are some mathematical tricks here. Why not first order quantum mechanics? Because of some physical problems, because generally we want that the potential should be free of zeros. So in the higher supersymmetric quantum mechanics, one can get this potential without singularities. So we can start the machine works, and we get the results easily. But of course, the calculations are not so easy as is given in the first order supersymmetric quantum mechanics. Now, first of all, I want to mention second order SUSY. Here, the very general form of the intertwining operator B has this form. You have the kth order, the differential operator. Here also we have H2 is the partner Hamiltonian of the initial Hamiltonian H0, and B2 dagger is the intertwining operator, which I told you. So K equals to 2 here. So then, if you look at the form of the intertwining operator, it is second order, because we were using just first order differential operator in the first order SUSY. Of course, this makes calculations more difficult. Now, if I use this H2 B2 dagger equals to B2 dagger H0, and if I use all the things inside of this relationship, I will get these three equations, especially the eta, the function eta prime. Eta prime is the derivative of function eta. So the V2 is the partner. It is the new potential. V0 is the initial potential. So we should solve these equations correctly, of course. First of all, if I look at my B2 intertwining operator relation, the eta x is the coefficient of my first order differential operator. I remember. So the gamma should be found in terms of eta and my initial potential. We can find it very easily. And if I use the first and third equations, I will get the gamma related equation again. And after some, the calculations shows that the best choice for the eta, finding eta, what eta is, giving an ansatz. So I give the ansatz, which is eta prime should be equal to negative eta squared and the other terms. Is there a pointer?
Press the middle one.
All right. It was easy, so I'm very excited. Sorry. Okay. Eta prime. So this is an ansatz. So I am using this ansatz, and I said that the beta is a function unknown, and this psi is a function unknown. This intertwining relation gives me this, right? So if this should be determined, so after some tedious algebra, I will get this relation, and I make it 0 of the coefficients of etas. Okay, for example, I make it 0 of that inside all these parentheses. If this psi prime is 0, then psi is a constant. So if psi is a constant, psi is equal to negative and positive square root of c. So this will also tell us more, but it is very simple. So I have this Riccati type differential equation, and I have an epsilon is the parameter. So I am giving this epsilon parameter. I keep this. I keep somewhere. This, excuse me, beta. It is very interesting that the beta can be written in terms of the ground state solutions. Okay, so if I use this beta in my previous relationships, I will get a Schrödinger's equation in that form. So if this is a constant, if you remember, I said that this should be a constant, and if this c parameter is 0 or not, this psi vanishes, or it is taking two different values. All right. So this u0 and u1, u2, etc. These functions are in Darboux transformations and in higher order supersymmetric quantum mechanics are known as the transformation functions. And there is the importance of the transformation functions in confluent supersymmetric quantum mechanics is very important because it helps the Wronskian of the system should be nodeless, right? So I keep this equation, and if I talk about more about my constants and my factorization energies, like this. So if I use them, so I can find a very close, a common solution for eta x. So let me talk about more about this coefficients or constant c. The real case, the c could be real, the c could be equal to 0 or negative. But I'm not interested in the complex energies here. So today I want to talk about the positive or equal to 0 case. In the positive case, this shows that it brings that the epsilon 1 should be different from epsilon 2, as you see here. Okay, so this is different. And the Riccati solutions of this star equation, this star equation is here. This is my Riccati equation. I call this equation as star equation. Then, yes, we have these two equations. After that, if I play with these equations by subtracting them, I can get the eta x function in terms of the Wronskian function. The Wronskian function, the components of the Wronskian function is my previous u1, 0, and u2, 0. These are the solutions of the Schrödinger's equation. Okay, so this is derivative of my Wronskian function and the function itself. So I found eta x. This is great. So this is why it is so great, because if you remember the previous, yes, the previous new potential, the generated or transformed potential relation, eta should be known, of course. So, if my Wronskian, if it has no zeros, then my partner potential, generated potential, has no singularities. So, this is the story in SUSY. higher order SUSY. Okay. If I look at the kernel of my operator, intertwining operator, and if I consider the Hamiltonian 2, the partner Hamiltonian of my initial Hamiltonian, so this eigenvalue equation, the solutions, explicitly we can get the associated to this eigenvalue, epsilon 1. If I use this, I will get this formula, and I already know that eigenvalue equation. Especially, this is related to the Jordan chain. So if I use that equation 2, if I use it in equation 1, I will get this beautiful equation. So I'm talking about the one can find the solutions of my H2, the partner Hamiltonian, easily using the kernel of this operator. And then one can arrive at the solutions. But these solutions are given, again, in terms of the Wronskian. So we can repeatedly, we can repeat all these solution steps again and again if we want to consider the third order and fourth order. But it will be very difficult, of course. So we have to generalize the whole story because it takes too much time and too much effort at the end. The other important aspect is of course, this operator is positive for every number n, and the order in the eigenvalues. The E0 is the eigenvalue of my initial Schrödinger equation, and epsilon 1 and epsilon 2 are my factorization energies. And if I consider if there is a thing like this order, especially if I use this order and if I use these numerical values for the epsilon 2 and epsilon 1, I can obtain this potential, V2, if I draw it in mathematics. So this is original harmonic oscillator, and this is my transformed V2 partner potential using second order SUSY quantum mechanics transformations. Right. Because in the first order SUSY, I cannot see such a condition. I only obtain the, yes, this is ground state, this is first excited state, and etc. And one cannot show the more and more complex things in the spectrum. In the confluent case is corresponding to the, if the constant is equal to 0. So my eta equation turns into Bernoulli equation. The eta is important because the new potential V2 is given in terms of my eta function. If I solve that equation, I will get eta x in a more simple form. So, the solution could be given here, and I can finally reach at the eta x. So this is the confluent approach to my original problem. So these are the, of course, for the modulus Wx, in order to get a modulus Wx, the boundary conditions are important. So this can be an example. This is taken from Fernandez's work. We can start with the Coulomb's potential. So this is confluent hypergeometric function. The solutions are given in terms of this. And we know the energy levels. We have quantum numbers, and we have this WR function. If you remember the previous, this R function can be obtained for my Coulomb problem. And one can get at the end V2 potential, the new potential generated or transformed potential with that form. Okay, so the UR is also given here. Okay, so it's very complex. So we can give such a graph for this original potential and the new generated potential. So this is the harmonic oscillator case. As an example, I prepared this example. I know all the things, all this story, this is very basic. So we can change the variable. We can give our Schrödinger's equation solution in terms of, again, the confluent hypergeometric function. And then I apply first order SUSY, and I get this error function solution for the specific values, of course. I think I forgot to give the specific values. A and B's are shown. But the important thing is this potential in the first order SUSY, the generated new potential, is the algorithm modus family of potentials. In the second order SUSY transformation, if I use this specific value for my factorization parameter, I will get the same results. But this is seen very rarely, because generally we always get more complex potentials at the end. Okay. So this could be a physical example for the higher order supersymmetric applications, because everybody asked me, so what's the thing in physics? So you are solving equations, and what is the importance in physics? The fermions problem, spin-off particles in the maybe on a curve manifold, the relativistic field equations can be solved using this higher order supersymmetric quantum mechanics. It's not so common, but why not? So the key order supersymmetric transformations. Last year, with my collaborator, we studied representations and integral formulas. And I can also show the other studies in this higher order supersymmetric quantum mechanics. Now, with Axel, we study a very generalized Schrödinger's equation. This is standard Schrödinger's equation, and these equations are also known as the Jordan lane. The Jordan chain is known as a very generalized linear independent eigenfunctions of a linear operator. Now, in the standard SUSY algorithm, yes, we find the solutions of corresponding Schrödinger's equation, but in the confluent supersymmetric quantum mechanics, our transformation functions are solutions, and these are corresponding to the Jordan chains. So Jordan chains, at the end, using these Jordan chains, we have a couple of differential equations if the value of k is equal to 2. For example, if we use j equals to 2, the Jordan chain length is equal to 2 here. So it is the most simple case to study. Of course, these are again corresponding to the solutions of our Hamiltonians. Again, standard Schrödinger's equation and the transform potentials. This is the kth order, higher order SUSY transform potential relationship. But these are also the transformation function solutions, the integral representations and the differential representations. In most cases, we saw that the integral representations are not so useful. But instead of them, using our Jordan chain, we use differential representations in order to get the point. So, we have a very general equation. So this is, I can't be sure that if this system is self-adjoint or not. If we use this very general mapping and point transformation, we will see that our Jordan chain could be modified as is shown, and also our transformation functions has this form. And finally, the transform potential, we'll get the form of the transform potential for the most general case. And here, we could have this fourth order SUSY transformation, for example. We could try this example. If we choose these functions, and if we choose a free, the potential, initial potential maybe 0, we can get this equation, but the iteration is very difficult. We are using computer program in order to calculate these Wronskian related formulas. So that's why we are choosing 0 potential or more simple potentials. For example, I remember that we tried linear potential, but the results were huge, really. For example, here, I can get the Wronskian if I try this all iterative calculations using my computer. I can get this Wronskian. And this Wronskian helps me to see the integral transformation equations in terms of area functions. But on the other hand, I want to show it is always very difficult to talk about equations using slides. So I want to show the paper of us. Yes. Yeah. We were interested in deriving the integral formulas for special functions. And the higher order supersymmetric mechanics is a wonderful tool in order to get the integral representation for the special functions for Laguerre, Hermite, and Jacobi, Airy functions, considering them. We can study all of them. Here, I was mentioning the At the beginning, I was mentioning the standard form of the Schrödinger's equation and point transformations. Especially, we can show the link between the confluent SUSY and the standard SUSY approach, considering the Schrödinger's equation. Now, the representation of the transformation functions starts here. I can show you some, yes, Jordan chains, related functions, and representations of Wronskian also. Yes. Let me show you another, yes, third order SUSY transformation. We can again select 1 over x squared potential, which is again simple, and fx and gx functions could be put into the very generalized Schrödinger's equation. So we just look at the very simple solutions of the original equation, which is given by equation 38. So 38 gives us the 39, and also the substituting this inside of my Schrödinger's equation, I will get the other function u1, and then I can restart to calculate the Wronskian function again. So I can get this result 42 for the Wronskian function. Especially, I want to show you the integral formulas and very huge integral formulas we can show. It was difficult to obtain them because we are using our handwriting and also computer, so we can compare each of them. So it was really difficult. All right, I want to switch to slides again. No. Ah, okay. So extended SUSY approach, confluence version of this algorithm is important to reduce the singularities or vanishing singularities problem in physics. Also, in the general case, we always get more complex potentials, but of course they don't look like the initial potential, of course. This is the general case. And also, one can generalize this problem using position-dependent mass. My recent study is position-dependent mass-related higher-order supersymmetry. Next month, I am finishing my study, hopefully. So this regularity of the SUSY transformations of potential, especially Wronskian of my transform functions, can give regularity of the SUSY transform potential. Especially in my study, I want to see that result, and I'm getting this result. Thank you. for your attention.
Any questions? So I should thank to Özlem Yeşiltaş. So
Thank
this is
you.
our first lunch break.
Okay.
We have to move to lunch. Okay, thank you.